time, but we are going to wait 2 minutes. Is that right, Jenny? Thanks.
Medyada farklı yayınlar yapar. Ne oldu? Bir bakın. Ana akım medya çok garip bir şekilde yönetim.
Welcome, everyone. We're going to get started in about 20 seconds and try to stick to a schedule. So this is the problem solving strategies in algebra from lab to practice symposium. Thank you all for joining us. Thank you to Jenny for co-organizing this and to Bella for hosting this. We will be joined later by John Starr, who will be giving a talk as well, and Martha Alibali, who will be the discussant at the end. So with that said, I will go ahead and get started. So I'm going to be presenting some work on missing operand algebra problems. This is work in collaboration with Rena Harsh and Sishang Pharma. So in this kind of spirit of lab to practice for the symposium, this will be kind of the most lab-like study that we'll be taking a look at. Fundamentally, what we're interested in this project is how do people think when they solve a problem like x minus 7 equals 2? So if you see a problem like this and you are, let's say, a graduate of algebra, then you might think, oh, it's 9 minus 7 equals 2. That's the number that goes there. And we call this a direct strategy in that you are sort of retrieving directly that arithmetic fact, perhaps because it matches this pattern. Alternatively, you might be thinking 2 plus 7 equals 9. This would be what we could call an inverse strategy. In this sense, you are performing the algebraic operation by isolating a variable. It involves some symbol manipulation here. In order to examine how people think about these problems, how they might choose which strategy, whether there's individual differences and flexibility in choosing between these, we make use of previous research on arithmetic verification trials. So for example, if I show you a problem like this, 2 plus 3 equals 5, and I measure how long it takes you to indicate that this is a true equation, and I interleave this with some false trials to keep you on your toes, well, prior research has found that people's response time to verify 2 plus 3 equals 5 as true is relatively fast, compared to their response time for 6 plus 8 equals 14, which is relatively slower. The important factor here between these two problems, has been found by decades of research, is the problem size. Here we operationalize this as the sum of the operands. This has been called the problem size effect. But in addition to the problem size effect, we also have seen from research that subtraction problems tend to take a little bit longer than addition problems, which raises a question. If you are answering a problem like this, you see x plus 3 equals 5, and you answer 2. If you're thinking 2 plus 3 equals 5, well, that's an addition problem. It has a smaller problem size, so you should be relatively fast. If you're thinking 5 minus 3 equals 2, well, that's a subtraction problem. It has a larger problem size and involves an extra step, so you should be a little bit slower. And if we measure your response time on these types of problems, we may be able to decode your strategy here. So that's the idea. So if I give you a problem like x minus 7 equals 2, by contrast to the previous example, and you indicate 9, if you're thinking 9 minus 7 equals 2, that involves subtraction and a larger problem size, so you should be slow. But if you're thinking 2 plus 7 equals 9, the inverse operation, that's addition and has a smaller problem size, so you should be faster. However, it does involve that extra step of performing this operation, so maybe you'd be not quite as fast, but still faster than if you went the direct route. We call this a switch benefit. In other words, in some problems, you will benefit more from switching to the inverse route. And if you're a flexible problem solver, maybe you're sensitive to this benefit. So our paradigm is to give people missing operand problems like you see on the top, measure how long it takes them to answer, and compare that to arithmetic verification trials. Specifically, we give both the direct and inverse match arithmetic verification trials for participants. And in total, we give 176 missing operand problems and all of the corresponding direct and inverse facts for the arithmetic verification trials. So that's a total of 128 matching true trials, as well as false. And we tested 59 undergraduate participants to see in a lab to see if we could learn about their reaction times. So I'm going to break down the results into a few different pieces. First, I'm going to talk about the arithmetic verification trials. So the question is, at first, do we replicate the problem size effect? Well, indeed, for the addition trials, we see each individual participant here is plotted their mean reaction time against problem size on the x-axis. And we see that participants tend to increase in reaction time as the problem size increases, as well as the overall trend across in aggregate across participants is significantly positive. For the subtraction problems, we see a similar result. We replicate the problem size effect across subtraction problems, again, significantly positive. And we can also take a look at individual participants. So instead of this aggregate correlation, what is the correlation for each individual participant here plotted as a dot between the problem size and the reaction time to solve the problem? And here we see all participants for addition trials are positive in correlation between problem size and RT. And most of these are statistically significant, and the overall median is around 0.3. And for subtraction problems, most participants are also positive, the median around 0.2. So we have replicated this problem size effect. So what about the missing operand trials? So again, we have x minus 7 equals 2, for example. In the addition trials, we see overall, if we look at problem size as a function of the individual operands, the known and the unknown added together, we see an overall positive trend for addition problems, indicating the problem size effect. So this suggests that maybe people are solving these addition problems by making reference to the direct facts. So they're recruiting similar thinking. This is a significantly positive effect. Notably, we see a little bit of a dip in RT around 10, so maybe due to practice effects with sums for 10. But we do see some evidence of individual differences, perhaps. And for the subtraction problems, we see no overall trend. There's no significant correlation here between problem size and RT, indicating something maybe more complicated or nuanced is going on. And again, if we take a look at individual participants' correlation coefficients, we see that most participants for addition missing operand problems have a positive correlation, positive problem size effect with a median around 0.2, although there's some variation here for the addition problems. And for the subtraction problems, we see that the correlation coefficients are centered around 0, indicating that, again, there's no clear relationship here, although, again, individual differences. So in order to understand these individual differences, we want to compare across these two tasks. We have the arithmetic verification tasks as well as the missing operand tasks. So let's take a look at the correlation coefficients for a given participant on both the arithmetic verification task here on the x-axis. So the stronger the problem size effect for arithmetic verification, the more positive on the right. And the stronger the problem size effect for missing operands, the more positive on the y-axis. And for addition problems, we see an overall positive trend here. So participants who are high on the problem size effect for arithmetic verification tend to be high for missing operand as well. And this is a significant correlation overall, although again, you see some individual variation, especially on the missing operand problem. And for the subtraction problems, we see there's no overall aggregate trend here, but individual differences, especially on the missing operand problem. So what we really want to know is, again, how do people think about these missing operand algebra problems if you can go either of these two routes? So in order to get at this, we performed a regression model for each individual participant, where we tried to predict their missing operand reaction time. So for example, how long does it take you to answer this question? As a function of the direct match reaction time. So in this case, that would be how long does it take you to answer 9 minus 7 equals 2? As well as this ratio of the direct over the inverse. So this is how long does it take you for the direct route divided by how long it takes you for the inverse. And we call this a switch benefit because the greater this number, the greater the numerator, the more of a benefit you would get from switching from direct to inverse. In other words, the more your RT should reduce. So as switch benefit goes up, your RT should go down. So there should be a negative relationship here, assuming you're sensitive to the switch benefit. So you have some flexibility between the two strategies. So let's take a look at the results of this regression. So again, we're going to plot each individual participant on here. On the x-axis, we have the t-value for the regression equation for that participant predicted by the direct match RT. And on the y-axis, we have that ratio of direct over inverse. So here are the results for all participants. And what we see is overall, there's a relationship apparent between the strength of direct retrieval. So here, as you go more positive, that means stronger relation between your missing operand RT and the direct match arithmetic verification RT, which is something we might consider a measure of fluency. So if you're more fluent with your arithmetic facts, then maybe that's what you're recruiting in thinking about these missing operand problems. On the y-axis, we see the more negative you go, that means you're reducing your RT as a function of this switch benefit. So you're noticing that going the inverse route will save you time, and so you actually end up with a lower RT. And so we see overall, there is a general relationship between these two. So this measure of fluency on the x-axis and flexibility on the y-axis. And it seems that some participants are both fluent and flexible, as kind of decoded by this method, whereas some participants might be more fluent but not flexible. And some participants are not well predicted by either of these measures. Finally, at the end of the experiment, we explained to participants what these two types of strategies are, and we asked them to estimate how often they use the direct and inverse operation routes. And what we found is that if we take a look at the percent of self-report of using the inverse operation and comparing that to the t-value for the switch benefit, which again measures that sensitivity to the difference in problem sizes, we see an overall significant correlation here where the more negative that switch benefit t-value, in other words, the more you save time by switching, the more often you do that, the more likely you are to self-report that you're using the inverse operation. So this kind of validates the decoding with the response time approach. So in conclusion, we replicate the problem size effect in the arithmetic verification trials, and we extended this to missing operand. Specifically, we find that addition problems might be, people tend to be recruiting that direct retrieval strategy, making reference, especially if they're more fluent in arithmetic equations, they can retrieve that more directly. Subtraction problems tend to be a little bit more nuanced. It seems like something more complicated is going on with those. And overall, we see these relationships between fluency and flexibility across participants with individual differences. So some participants are both fluent and flexible. Others may be perseverating more on one strategy or the other, and that's maybe why we're not picking up on them in this decoding strategy. Finally, we validated this approach with the self-report. So we see at least some correlation there between flexibility and self-report of using the inverse operation. What we'd like to do moving forward is explore individual differences more, especially for those that we're not able to decode with this method. And to that end, we are waiting on standardized math scores that have unfortunately been delayed due to COVID, but for these participants, we'll be able to assess whether this helps predict whether they're higher in the fluency or flexibility measures. So that is it, and thank you to these people for helping with this project. And I'm happy to answer a question while we wait for the next speaker, who is Jenny Chan. Yes. I see
Hi,
a question in the chat.
yeah.
Hi.
Great presentation, really interesting.
Thank you.
My question may not actually matter. I think that the cross-domain, the cross-operation correlations are, that's obviously the really interesting part of this. But when you defined a subtraction problem like 9 minus 7 equals 2 as a large problem, I mean, that's not how I would define a large subtraction problem. I define it as like 16 minus 9 equals 7 or something, which would correspond to what the large addition problems would be. So can you kind of explain to me, I think what you mean by problem size is a little bit different than the way I would think about it.
Sure. Yes. So that's a great question. And I'll try to give a quick answer right now. We can talk more about it at the end. But we basically are defining large relative to the smaller problems. And because our paradigm, we only allowed for a single digit response in order to keep the RT measure the same across all of them, we were kind of constrained in what that first operand could be. It had to be a single digit. But I know there has been work showing this with much larger operands like 50, for example, and that is something that, that we want to compare to. But in our case, we're really constrained by the method to look at single digits, but I think it would be interesting to look at multi-digit and somehow control for that.
Yeah, it's got more to do. Yeah, I see what you mean now. It's got more to do with what people are actually doing, though, because it seems pretty likely that. So if you have a problem like 9 plus 7 equals 16, that's much less likely to be solved by retrieval, whereas 9 minus 7 equals 2 is much more likely to be solved by retrieval. So in essence, you haven't really manipulated problem size in the sort of traditional sense, right? You've really, anyway, I would, that might be why your correlations look weird, I guess. But anyway, enough. Okay. Thank you.
All right, thank you. Yes, great point, thanks. All right, Jenny.
All right, okay, let's see. Okay, hi everyone, I'm Jenny, and today I'll be presenting some findings on the association between pause time and strategy efficiency in middle school students' algebra problem solving while using an online math learning tool. There are often more than one way to solve a math problem. For example, in this equation, we can solve it by distributing the 3 into parentheses, or to divide both sides by 3 first. These two different strategies require different numbers of steps, and the second strategy is more efficient in terms of the steps, but it requires us to notice the multiplicative relation between 3 and 18. So what are the factors that predict or influence students' strategy efficiency? Prior work has shown that students' math knowledge, math anxiety, and self-efficacy all influence and contribute to students' strategy efficiency. For instance, John and Bethany's prior work has shown that students with higher math knowledge tend to use more efficient strategy to solve algebraic equations, whereas compared to students with lower math knowledge. Other work has also shown that students with higher math anxiety tend to implement less efficient strategies to solve arithmetic problems compared to students with low math anxiety. In addition to these factors, we hypothesize that pausing may allow students to notice the structures like the relation between 3 and 18 in the equation earlier and plan for efficient strategies. And pause time in online learning context has been used as a behavioral indicator of thinking, and it positively predicts students' problem-solving strategies. So in this study, we statistically controlled for students' math knowledge, anxiety, and self-efficacy to estimate the independent effect of pause time on students' strategy efficiency. We used the data collected within From Here to There. From Here to There is an online dynamic math learning tool where students can manipulate expressions using actions like clicking on the addition sign to add the numbers together or dragging the numbers together to combine them. In this game, students are presented with an active initial expression and a mathematically equivalent goal, and the objective is to transform the expression to match the goal. Here, notice that we're not simply asking students to add all the numbers together to simplify the expression. To efficiently reach the goal, students actually have to notice the structure between the two expressions and find an efficient way to transform the expression. So for instance, here students can click the addition sign to add the numbers together or drag them together. And if 27 is not really helpful to get them to reach the goal, students can reset the expression at any time and retry their transformation. So here we can decompose 10 using keypad to substitute it into 5 plus 5. We can drag 7 and 8 together to add them, and then we can drag the 5 to commit to reach the goal. And in the system, we timestamped and recorded all students' actions, so we can analyze the amount of time students pause before they take their very first action and the numbers of steps that they take to reach the goal. And here are some examples of the data that we get from the system. So here in this example, the student first take 1.5 seconds before taking their first step. They take 3 transformation steps to reach 12 plus 15, reset the expression, and then retry the problem and eventually take 3 steps to reach the goal. We classify all the steps prior to the final solution as the exploratory steps, and the steps that they took in their final solution as the solution steps. If students didn't reset the expression and retry it, but instead reach the goal on their first attempt, all their steps are classified as solution steps. Because the problems vary in complexity, we calculated the percent of the total problem-solving time the students took to pause before their first action and use the percent pause time in our analysis. Because students can reset the problems and retry them, we separated our analysis based on whether or not the problems are solved on their first attempt. For the problems that students completed on their first attempt, we asked, does the initial pause time before first action predict students' solution steps above and beyond their math knowledge, anxiety, and self-efficacy? And for the problems that students completed after multiple attempts, we asked, does pause time still predict students' solution steps on their final attempt above and beyond their exploratory steps prior to the final attempt, their knowledge, anxiety, and self-efficacy? And finally, we asked, is exploratory step a potential pathway through which students' initial pause time influence students' final solution steps? The data came from a larger intervention study where we test the efficacy of 2 educational technologies, and half of those students received From Here to There as their intervention. 286 middle school students completed a pre-test that measures their math knowledge, anxiety, and self-efficacy. And they received 4 30-minute intervention sessions where they solved problems within From Here to There. They started with problems on easier ideas like the basic operations like we saw earlier, and worked their way up to more complex ideas like orders of operation and inverse operations. And students worked on these problems at their own pace on their own device during their instructional periods. The 286 students together completed a total of 11,119 problems. On average, students completed 40 problems across the 4 sessions. Out of these 11,000 problems, 7,600 of these were completed on the first attempt, and almost 3,500 of these were completed on the final attempt. Before we dive into the primary analysis, I just want to provide a quick overview of the data on the student level. Remember that students completed about 40 problems in From Here to There. So we average across the problems to get the student level value for the variables within From Here to There. So that's the pause time, there's solution steps on the first attempt, solution steps on the final attempt, and the exploratory steps. And so here, and then here the means of the grading mean pulled across the students. So here we see that on average, students take about 42% of their total problem solving time pausing before taking their first action. And we found that this pause time is negatively correlated with students' solution steps on their first attempt, solution steps on their final attempt, and their exploratory steps within the game. So students with longer pause time tend to take fewer steps and more efficient strategy in problem solving compared to students who have shorter pause time. And students with longer pause time also tend to have higher math knowledge and lower math anxiety, although these correlations are fairly weak. Now, to answer our primary research questions, for the first two research questions, we conducted a mixed effect linear regression model to test the association between pause time and solution steps. In these mixed effect models, we included problems and students as random effects to account for the fact that the same problems were given to all the students and students completed different numbers of problems. To aid the interpretation of the findings, we mean center the student level variables at the student level and the problem level variables at the problem level. And to address our final research question, we conducted a mediation analysis to test whether exploratory steps may be a potential pathway through which pause time influence students' final solution steps. So here's the finding for our first research question. We found that after controlling for students' math knowledge, self-efficacy, and math anxiety, longer pause time is associated with fewer solution steps, so more efficient strategies on students' first attempt at problem solving. And we found the same similar pattern for students' final solution steps. So after controlling for students' math knowledge, self-efficacy, math anxiety, and their exploratory steps prior to the final solution, we found that longer pause time on the problem is associated with fewer solution steps on students' final attempt at problem solving. Now, the first step of the mediation revealed that here at the problem level, after controlling for students' math knowledge, anxiety, and self-efficacy, pause time still predicts students' final solution steps. And exploratory steps and the indirect path through exploratory steps is significant. So on any given problem, a longer pause time is associated with fewer exploratory steps prior to the final solution, and fewer exploratory steps is associated with fewer final solution steps. Interestingly, the direct path between pause time and final solutions steps remains significant. So in summary, we found that longer pause time is associated with more efficient strategy. This is true even after we control for math knowledge, anxiety, and self-efficacy. And we observed this association on students' first attempt at problem solving and their final attempt at problem solving. We also found that even after accounting for the indirect path through exploratory steps, pause time still seems to have direct influences on students' final solution steps. And so for our future directions, we would love to examine the potential cognitive processes underlying students' pause time and the mechanisms through which pause time may influence students' strategy efficiency in problem solving. So with that, I would love to thank you all for coming and thank you for your attention. And I'm happy to take a couple of quick questions as we transition to John's talk. Thank you. Awesome. Maybe we can save the interesting questions later for the open discussion. And then I see that John's here, so go ahead, John.
Thanks, Jenny. Hello, everyone. So is the idea here is that I'm going to share my screen and yeah?
Yes.
Okay, so let's see if I can get this to go. All right, can everybody see?
Yes.
Yeah. Okay, well, welcome to this presentation. I'm John Starr, as you heard, and on behalf of my colleagues, Kelly Durkin and Bethany Rittle-Johnson from Vanderbilt University and Abby Lohr at the Washington University of St. Louis, I'm excited to talk to you about our work on the effects of comparing and discussing multiple strategies on students' algebra learning. So just a brief intro. Algebra learning, we know, is very difficult for students for lots of reasons. It's increasingly abstract as compared to arithmetic. It requires students to have some facility with multiple representations. And it requires understanding of both key concepts and some ability to understand and use some strategies for solving problems. This proficiency manifests itself in both procedural knowledge, conceptual knowledge, and procedural flexibility, all of which I'll talk a little more about in a moment when I think about how we're doing our assessments. We feel that one way that student learning of algebra, despite these difficulties, can be improved is through the comparing and discussing of multiple strategies. The benefits of doing so, especially of comparison and discussion, are many, but I've listed a few here. First, comparison is linked to improved adaptivity to unfamiliar problems. Comparison has been found to improve learning in many domains. And comparison and discussion also promotes knowledge integration and generalization, again, across several different domains. So we think comparing and discussing multiple strategies is a very promising instructional practice, but its implementation is quite challenging, has been found to pose significant challenges for teachers. These include that teachers have limited experience with discussing and comparing multiple strategies, as well as that teachers have difficulty in the moment spontaneously generating effective explanation prompts, as well as things to be compared. So we set out to design a curriculum that supported teachers' use of comparing and discussing multiple strategies that might address some of these implementation challenges. Our curriculum, we call it CDMS, that's for comparison and discussion of multiple strategies. It is a supplemental Algebra 1 curriculum that's intended to provide increased opportunities for mathematical discussion through comparison. So in this curriculum, the teacher is provided with some information about multiple strategies for solving problems, and this allows the teacher to anticipate and monitor and select and sequence and make connections amongst those multiple strategies in the form of a discussion. To the right, I am showing you a piece of what we call our implementation model for our curriculum. So this is something that teachers learn how to do when using the curriculum. And you can see that it involves both comparison and discussion. And this is about recommended, say, 20 minutes in the class where the teacher goes through this particular protocol to enable students to make comparisons and then to discuss them. The basic curricular unit for this curriculum is what we call a WEP, or a worked example pair, and the prompts that are associated with it. So let me just show you one of these WEPs and talk about it. So to the right, you see an example of what is, again, the basic unit of this curriculum. In this, you see that there are two hypothetical cartoon characters. In this case, they're named Gloria and Tim, are solving the same problem, and they do it in two different ways. And we also see their dialogue indicating the ways that they approach the problem. If you look at the upper left of that page, it says which is better, and that indicates that this type of comparison is considering two different strategies which may differ in which one is better, and that's what the students may be discussing here. But there's other types. You can see on the left, which is correct, might compare right and wrong answers. There are two other types. Why does it work? How do they differ? And each of these WEPs is followed by prompts for explanation, that means questions that teachers would be asking, and also a structure for pursuing these questions. In particular, we make use of a think, pair, share instructional routine. So we have this supplemental curriculum, and we wanted to see if it improves students' learning of algebra. So we did this study that I'll describe, where we compared students using the CDMS curriculum to those in more typical algebra instruction to help us understand more about how discussion can support effective comparison. In this presentation, I'm only going to be focusing on one unit of the curriculum, the first unit, which was a unit on solving linear equations. The students that we worked with were students from the Eastern United States, and in the treatment group, we had 16 teachers and their students. They worked with the WEPs and had some professional development, which I'll describe in a moment. In the control group, as a business as usual control, we worked with 13 other Algebra 1 teachers. Algebra 1 is taught in many US schools in the 8th and the 9th grade, and our teachers were split across the 8th and the 9th grade. We gave the treatment teachers some professional development. In particular, they worked with us for 1 week. It was about 35 hours of professional development in the summer, where they were introduced to the curriculum and the implementation model of CDMS. In addition, they did a lot of time practicing the teaching of this model and also viewing video exemplars of others using this model. In terms of other things that other features of the study, there was a unit pre-test and a post-test that was given. And in addition, we videotaped all the teachers in both the treatment and the control in their implementation. The teachers were videotaped 2 or 3 times for each unit. We did 2 sorts of analyses on the videos. So we did what we call a general fidelity analysis of the videos, where we looked at 2 videos for each teacher in the treatment and the control, and we measured whether they were using instructional practices that were consistent with the CDMS approach. We would have expected the treatment teachers to do so because they engaged in the professional development, and we would have expected the control teachers not to do so, but we measured this instead. We measured this to see. And then we also subjected the treatment teachers to another instrument, a treatment quality instrument, where we looked at 1 video and we measured the quality of their implementation of the CDMS materials. And as I mentioned a moment ago, we had a unit assessment pre-post, and we measured conceptual, procedural knowledge, and flexibility. I just want to show you a couple of examples of how we were measuring procedural and conceptual knowledge here. So I'll just pause for a few seconds so you can look at this slide. Sorry. And then here's an example procedural flexibility item. And the ways that we're conceptualizing procedural flexibility are based largely on my prior work, where we define procedural flexibility as knowledge of multiple strategies and the ability to select the most appropriate strategies for a given problem-solving circumstance. So we did multi-level regression models to look at the effects of the instructional practices and that we measured in the fidelity instruments, as well as condition, on students' post-test scores. And let me tell you what we found. So first, in terms of general fidelity, again, this was the instrument we looked at video of both treatment and control teachers to see whether they were using practices consistent with the treatment. We expected the treatment teachers to be doing so and the control teachers to not be doing so. And that's largely what we found. So we found that the codes that you see to the right there were high for all or most treatment teachers and rare or less likely to appear in control teachers. The only thing that control teachers were doing a little of is that bottom blue box where they were, it's not in a box, but the next to last one, the small partner group discussion, we found that 42% of control teacher lessons did include some partner work. But with that said, we found that students who had more exposure to multiple strategies, that's the green box, as well as students who engaged in a relatively sustained period of class discussion. And for us, this is actually a very modest kind of definition of sustained class discussion, it's only 1.5 minutes at least, that those students did better in the post-test. So that did give us some evidence that our practices were producing the kinds of effects that we were looking for. In terms of treatment quality, which was the other video coding system we used for treatment teachers only, we measured treatment teachers' performance in these 5 areas: supporting procedural flexibility, making sets of procedures, and then teacher questioning, student responses, and opportunities for interaction. The scores you see are mean scores out of 4. And so overall, this is sort of moderate implementation quality. It sort of shows that this is actually very hard for teachers to do well. But we had some evidence that things like supporting procedural flexibility and making sense of procedures were, and to some extent teacher questioning, were things that teachers were starting to do. We did see some examples of high quality implementation, and when we saw those, they highlighted the importance of asking conceptual and open-ended questions, including asking students to rephrase. We're not going to do some further analysis on this just because we only looked at 1 video per teacher in this particular coding. And the results of the Unit 1 assessment were also quite promising. So first off, we didn't find a pretest difference between the conditions, which is good. But at post-test, we did find in the green box there that treatment students had a higher total unit scores than the control students. So that is some evidence indicating that our intervention was effective at improving student learning. If we break down our assessment into the 3 subcategories of knowledge, conceptual, procedural, and flexibility, then you can see that this effect may have been driven by higher scores in the procedural flexibility test, although we urge some caution in that just because the test was designed to be looked at as a whole, and it doesn't have sufficient reliability to break it apart in that way to do separate analysis. So finally, these results we feel do indicate or suggest that treatment teachers engaged in sustained comparison of multiple strategies, small group work, and whole class discussion, as we hoped they would as a result of our PD. That in their teaching, the teachers did focus on making sense of procedures and developing students' procedural flexibility, and that doing those things had the result of producing students with higher total unit post-test scores than control students for this 1 unit. We take away from this that frequent comparison and discussion of multiple strategies has the potential to increase students' algebra learning, and that's a very exciting result for us. So thanks to our funders for supporting us, and this is who we are. And we hope to see this paper out soon in press. So I'll pause there. And are we turning things over to Martha next, or any questions? What should we do?
We can do a couple of quick questions if there's any, and then can transition to Martha.
All right, well, it looks like we're passing it on to you, Martha.
Okay. Can folks hear and see appropriately? Yes. Okay, great. Just get the people out of the way. Okay, so thank you all for 3 really excellent talks. Also, thanks to each of you for sending me your slides in an early point in time so that I had time to actually reflect about them before preparing these remarks. I want to, let's see, I want to emphasize that what we've heard today, all 3 talks focused on problem-solving strategies in algebra. In one talk, we heard about strategy choices for missing add-in problems. In one talk, we heard about strategy efficiency for expression transformation. And in one talk, we heard about supporting multiple strategies and procedural flexibility generally for linear equations. And I want to note that one theme that runs across these 3 areas is the idea of procedural flexibility. This idea that there are multiple ways to solve a problem and that some ways might be more appropriate for a given problem or in given context. This is an idea, that John, among others, has been talking about for a number of years. And I want to highlight some of the issues that this set of talks raises about procedural flexibility. How do we conceptualize it? Who demonstrates it? How does it manifest in students' behavior? And how can we support students' acquisition of it? So the idea of procedural flexibility has been talked about largely in terms of adaptivity to specific problems. But when one looks at the literature and really thinks about it, a lot of this idea of adaptivity is really couched in terms of the idea of efficiency. The idea is that skilled problem solvers have the ability to deploy procedures in ways that let a maximally efficient solution be generated for a given problem type. And that's certainly true in the talks that we heard about today. There was a lot of focus on efficiency of what students are doing. For example, reaction time on the missing addend problems. The switch benefit is really about an efficient approach to solving the problem. Or the number of steps in transforming an expression. The focus here is on planning ahead so that one can have an efficient path to the goal. And so I just want to talk for a moment about each of this thread of efficiency that kind of runs through these talks. In the work by Bai, Harsh, and Varma, as you know, the focus was on missing addend problems and their relation to arithmetic verification. And there were two potential strategies that students could use. The heart of the matter here was this idea of the switch benefit. Was there a benefit for people in solving subtraction problems, in particular for switching to a more direct arithmetic strategy? And the idea here in this work, which I thought was really fantastic, was that this idea of switch benefit could be assessed at an individual level for each individual participant as an index of that participant's recognition that the switch for that individual's skill was actually effective for that participant. And so as an index of flexibility, this also correlated with self-reports of switching the strategy, suggesting that it really is a valid measure of thinking about this switch. And I think what was important here is to think about the different profiles of people with respect to this idea of switch benefit. And Jeffrey talked about some of these as he discussed the findings. There were some participants who were fast and sensitive to the switch benefit, some people who are fast but not so sensitive to the switch benefit, and some people who were not so fast and also not really so sensitive to the switch benefit. In some discussion we had offline, Jeffrey mentioned that, perhaps those individuals are not yet appreciating inverse thinking or recognizing this potential benefit of switching at this moment, that this may have to do not just with fluency, but also an appreciation of the inverse operations and how they relate here in these missing addend problems. All right, Chen, Amar, and Lee also focused on this idea of efficiency in their work on planning and pausing in expression transformation. They considered multiple individual difference factors like math knowledge and as well as affective factors, but they looked also at a specific overt behavior and found that both math knowledge and pause time were associated with use of fewer steps in their expression transformation task. And so this raises a really interesting question, what happens in the pause? It's sort of like what happens in that little reaction time moment in the Bai work? And what happens in that moment? What's going on as a student tries to navigate this situation? The student may be deciding what strategy to use. They may be looking again at the target, making sure they've encoded it properly. They may be evaluating an interim result. So we can think about what might be going on in that pause term in terms of a range of different potential processes that may be deployed differently by different students or in different contexts. These all might contribute to this kind of flexibility. So trying to understand not just that pausing matters, but what actually are students doing in their pause, I think is something important for us to think about. If we are thinking about what's happening in the pause, that might also give us insight into what processes we can support in students. So do we need to support students effectively encoding the target or considering the set of alternatives or having some basis for choosing among the strategies. What are the targets that we would like to support? And this brings us to the third talk. What should we encourage students to be doing in that pause? Well, maybe we should be encouraging them to think about the strategies in ways like the teachers and students in the Starr, Durkin, Rittle-Johnson, and Lehrer work suggested. In their intervention, which was very effective at promoting reasoning about linear equations and especially procedural flexibility, what they did was they exposed students to multiple strategies through these WEPs, these work example problems. And what they did was encourage flexibility through discussion and comparison. So how do the strategies differ? Why does each strategy work? Which is better? These are the kind of things that maybe people are considering in the pause, or maybe people are considering when they look at those missing add-in problems, deciding, what way to go. And so this raises, I think, an interesting and important question for us as a field to think about: what does it mean to be better? As I mentioned at the outset, better can be operationalized in terms of efficiency, and that is something that we often do. But I think, there are many other things besides efficiency that people might bring to bear when thinking about what strategy to use. So does the strategy make sense? How common is it? Is this something I see lots of people doing? Is it complicated? Do I remember it well? Is it going to take me a long time? And so I just want to share a couple of quick thoughts about a study that we're currently working on, where we actually asked people to evaluate strategies on lots of dimensions, and then looked at whether their later use of those strategies depended in particular on efficiency or on some of these other qualities of strategies. We did this with college students with constant change problems. I'm not going to get into the details. I can save that for another talk. But I just wanted to observe efficiency was associated with greater likelihood of later use for both of the target strategies we examined. So students who evaluated the strategies as more efficient were more likely to use them later. But this was also true for other dimensions. So like intuitiveness, if students rated strategies as more intuitive, they were also more likely to use them on later problems. And in fact, when we compared the different kinds of dimensions, we found that intuitiveness was actually a stronger predictor of later use of the strategies than efficiency. Efficiency was positive, but not significant when we controlled for the other rated dimensions. So you can stay tuned, and maybe at the next MCLS, we'll tell you more about that line of work. But all right, I just want to highlight, in light of that, a couple of remaining questions for future work. First, this question, this thread of individual difference factors, I think ran through some of the talks. What individual difference factors are associated with this kind of flexibility? Variations in math knowledge? Yes, we saw that in multiple talks. Affective factors, in the end, they were correlated in the Chen et al. Work, but in the end, they were not part of the significant prediction of efficiency in the final models, I believe. There may be other factors like need for cognition or social cultural factors that may also speak to flexibility. There might also be differences in individual participants' values. What do they value about strategies? Maybe you're a person who loves shortcuts and you want to do everything the fastest way, but maybe you're a person who cares about like deep understanding and you only want to use a strategy if you really get why it works. So those things might be relevant individual differences as well. And finally, I just want to raise a question about this idea from lab to practice, which was one of the themes that we wanted to bring out in this symposium. We've thought here today about, what processes we should target in helping teachers and students acquire procedural flexibility. And the intervention that John talked about had lots of different components. Students discussed which is better, how they're different, why each strategy works. I'd like to suggest that it might also be important to help students think about how strategies are related, that understanding these connections across strategies, how different strategies achieve the broad goals of solving the problem in different ways, but ways that may also tie together, may be especially important for helping students build conceptual understanding. And I just want to highlight Pooja Sidney has been doing a little bit of work, how this plays out across different problems of a similar type with different kinds of numbers, like whole numbers and fractions. And I think here in the work that we talked about today, there's opportunity for thinking about how different strategies for solving the same problem might also relate, and how thinking about those relations and how we can support students in grasping them and teachers in communicating them can help us come a long way towards having those rich discussions of strategies that help inform what students will do when they pause to decide what to do. All right, thank you. And I hope we can have some general discussion. All right.
Martha, thanks for pulling everybody together and kind of tying it all together. I think this is something that's really neat to see the three approaches with totally different kind of practical implications, but also methodologies used. One question that I think about a lot, and I think came up today, is measurement and thinking about how to assess these things at scale, either in the lab or in the classroom, and finding kind of a happy medium of being able to measure variables that are typically done through kind of repetitive laboratory tasks and moving them into classrooms where you may only have 5 minutes to assess something from afar for virtually. So do you have any thoughts on like the ways that we can kind of take some of these metrics and move them from something that can be done through kind of precise cognitive tasks and move them towards classroom practice? Because I know John and I have talked at length about how items are only as good as what students report, and that it's often difficult to get at the types of things we're trying to get at through a multiple choice item.
Right. I mean, I think the remarks John made about the assessment that they used for the unit are well taken, that deconstructing it into conceptual and procedural and flexibility kinds of measures might not actually be warranted, given that there were not very many items, et cetera. On the other hand, for teaching purposes, we want to understand what it is that students know. And so performance on the unit test is not clearly the only way that we learn what students are thinking about. And so I think the idea that these mathematical discussions were being fostered in that work is also an opportunity for a place to really look at the kinds of connections that are being made, both in the small groups and in the class as a whole. And as instructors, as teachers, what kinds of things should they be looking at and supporting and pulling for in those kinds of discussions? How do you get the discussion to move towards that rich sort of conversation? I'm sure that was part of the focus of the intervention. Maybe John, you could comment on how that was implemented and how teachers could tell whether they were being successful.
Yeah, it's definitely something we've been wrestling with. I think in this project that I was just describing, it felt like we were thinking more about how we would assess teachers' instructional practices that could be used to support students' flexibility, and maybe thought less about how we might assess that flexibility in students. So certainly I think that is a direction we kind of want to head next, is figuring out what are some more sophisticated ways that we can assess students' flexibility. But for us, in looking really at teachers' instructional practices, even that is very much non-trivial. If we were thinking like, what does a good discussion look like, and what are the features of a discussion that support procedural flexibility, that's really tough. And so we sort of have spent a lot of time trying to think about that, and we're not the only ones thinking about this. We've sort of drawn from others' measures as well. But it seems like that if you're interested in developing students' procedural flexibility, then we do have this vision of what a good discussion looks like and what that discussion is about. But it's I don't think we're to the point yet where we have excellent measures of that that are easy to use. It turns out to be a very nuanced thing to look at, and thus very expensive to code for.
I mean, I guess on that same sort of theme, I think about understanding when and why flexibility is manifested. You know, I suspect in the college students in the study that Jeffrey presented, I suspect they all could implement the inverse strategy. Why is it that some students choose not to? Does it have something to do with, you know, their views about what they're expected to do in the task? Does it have something to do with their personal values about what kind of approach should be used in a given moment? You know, understanding, you know, in that particular case, I don't think it's the case that the students don't have that strategy at their disposal. And so understanding why they choose not to do it, I think, is an important question.
Yeah, I agree, and I think it's interesting to think about the mathematical domains that you choose to use when you're trying to answer these questions with students. And so, for example, if you are working with college students, then what are the pros and cons of using an arithmetic type problem to assess their flexibility? And is there another kind of domain that you could use that's a little more recent or new, where perhaps the benefits of using an alternative strategy might be more marked, more significant in their mind. And so I think that's tricky. And that's sort of why we've sort of stuck around in the algebra space for so long, is because we feel like that we can work with students, and these strategies are they're sort of in the moment strategies that as they're learning algebra, they may say, oh, that's actually very useful to do it this way. And that might enable us to move forward. But I'm not suggesting that doing elementary mathematics with college students is not useful as an arena for studying flexibility. But I think there's just some interesting questions to ask about which domains we choose to use and what affordances and constraints those choices in domains bring us for measuring flexibility.
Yeah, I certainly agree with that. I think it would be in part interesting to use something like our paradigm with students who are in the middle of learning between these different strategies, which is somewhat a future direction we'd like to go. And as well with undergraduates, that it would be interesting to see how they solve more complicated problems, especially given that a lot of the people we recruit aren't necessarily currently taking math classes, but they obviously had been taking math up until somewhat recently, and it would be interesting to you know, extend that further. Thank you.
All right, I noticed that it is 12:02, so I don't want to keep people around for too long. Thank you all for coming, and I would like to thank Jeff, Martha, and John for helping me put together this symposium and for contributing. And please feel free to reach out if you have any questions. And yeah, again, thank you.
Thank you, Jenny.
Well, thank you everyone for being here. We're going to meet again next Thursday, and we'll be talking about environment. We'll be talking about SES, parental behavior, and schools, and how they influence mathematical brain. So I'll see you all next week. Thank you.